Great. So what we're going to talk about today is estimating the area under a curve using Riemann sums and fixed number of rectangles. So the example that we're going to do is for the function x squared minus 2x plus 1, and we're going to find the area under the curve between x equals -2 and x equals +2 using 8 rectangles. Now, I chose 8 for this particular example so that the numbers come out nice and we don't have weird, crazy fractions. But this general procedure certainly will work even if you end up with weird decimals, because the number of rectangles is a strange number. Now, I want to first just look at the graph that I've made here. This is our x squared minus 2x plus 1 function, and its graph between -2 and 2. It's bounded below by the x-axis. And there's a couple of different ways that we can go about estimating the area under the curve. And so before I actually do the calculation for a couple of these different methods, I want to talk about the way that these problems tend to get asked and how they conceptually differ from one another. And then we will go ahead and do some of the worked examples. Now, there's basically 5 ways that problems like this tend to get asked. So there's the right-hand rule, the left-hand rule, the midpoint rule, lower bound, and upper bound. And for certain kinds of functions, some of these will merge together. But for a function like this, they are technically distinct. So let's look at the right-hand rule, and I've created a graph. Again, this is just a copy of the same graph. But what I want to do is I want to draw on here what the right-hand rule would entail. Now, with 8 rectangles and we're going from -2 to 2, let's so just write this map out just a little bit. This will be relevant for our calculations later, but delta x is equal to b minus a over n. And in this example, b is 2, that's the right endpoint, minus a -2 divided by n equals 8, which is going to get us 4 over 8, which is a half. So our step size is a half. And so starting then at -2, we can see these grid lines here are the 1/2 step. And so that's where we're going to draw our rectangles. Now for the right-hand rule, our rectangles are going to have the height of the graph on the right side of the rectangle. So if we draw this rectangle right here, we're going to have this width, this 1/2 width, and then the rectangle will go up to where the graph hits on the right side of that rectangle. And then the height is designated by that point on that right endpoint. And then when we do the next rectangle, we go up from the right side of the rectangle until we hit the graph. And then that is the height of our next rectangle. Right-hand rule, estimate, right-hand rule, estimate, right-hand rule, estimate. This has no height, so our estimate is just 0 height. And then right-hand rule, estimate, and then right-hand rule, estimate. Now, depending on, you can see, depending on whether the graph is increasing or decreasing, then the right-hand rule will become a slightly overestimate or slightly underestimate. In this particular example, it is an underestimate on the left side of the graph, but it is an overestimate on the right side of the graph. But that's the right-hand rule, and it's very methodical. It's easy to calculate. This is one of the examples we're going to calculate later, because you're always picking the right end of the graph. And so you don't actually have to pay attention to the graph as much, because you're always just choosing the right end point to where you estimate the height. And again, the procedure for estimating the area here would then be to calculate the area of these rectangles. They have a base of 1/2 and the height based on the size of the function on the right-hand end of the rectangle, and then you add them all up. Now, the left-hand rule differs in the fact that you don't take the right end of the rectangle, you take the left end of the rectangle. So for this first rectangle, the height calculation that we're taking is the left end. And so this is our rectangle. And then for the next one, the next rectangle, you take the left end and you estimate, hopefully with a straighter line than that. And then the next one, you take this one. And then the next rectangle, you take again this left end. So again, notice we're getting overestimates on this one on the left side. And then the left end is flat here. And then the left one is an underestimate on this side. So again, the idea here is that, again, it's very systematic. These are relatively easy to calculate without looking at the graph, because you're always just taking the left end. But if the graph is decreasing, then the left end will tend to produce an overestimate. And if it's increasing, it will produce an underestimate. And this graph is a combination of under and overestimate. So because the graph is not monotonic. Now, in the midpoint rule, this can be done somewhat mechanically, although it does require more computational steps. But the idea of the midpoint rule is that you take the height of the graph at the middle of the rectangle, the middle of the region that you're breaking it up into. So in this case, the rectangle is here, but we want the height to be dependent upon the height at the middle of the region. And then same thing for this one, the height is here. And so that is our estimate. The midpoint is here. And so again, that is our estimate, midpoint of the region. Now, the midpoint is a little bit more complicated to calculate mechanically. But as you can see, it tends to be sort of partially an underestimate and partially an overestimate in each rectangle. And so that means that it's probably going to get a slightly better approximation, regardless of the direction that the function is going in, than either the right-hand rule or the midpoint rule, or the left-hand rule. And so this does tend to do a slightly better job, but it is a little bit more complicated to calculate from a mechanistic standpoint, from a procedural standpoint. But it's not too bad. But the benefits may outweigh the limitations. And then finally, we have two other ones, the lower bound and the upper bound. Now, as we noted, if your graph is monotonic, then the lower bound will actually be the right-hand rule or the left-hand rule. And if your graph is not monotonic, then you have actually a different calculation strategy. So in the lower bound case, you're always going to take the lower end of the rectangle. So in this example, on the left side, we're always going to take the right hand. You go up from the right-hand side. That's the lower bound of the area. And we just always choose that until we get to the part where it's increasing. And then we have to choose the left-hand rule. Now, what this will produce in this case is an underestimate, a consistent underestimate for the area. Now, the theorems, as they get proved, we have a lower bound and an upper bound, and they converge as the number of rectangles increases. That's sort of that squeeze theorem idea. It's part of the idea of proving that there is a limit when you take more and more n. But if the graph is decreasing all the time, it's always the right-hand rule. They're just equivalent. And if it's always increasing, then it's always the left-hand rule for the lower bound. But when it's changing direction like this, then you have to physically look at the value on either side of the rectangle and then pick the appropriate one. And then the upper bound works similarly, except that now you're always choosing the point of the rectangle where the height is the largest. And again, conceivably, if you have a rectangle that has a maximum in the middle of the interval, you will take the middle of the interval wherever that maximum occurs and not one of the ends. So these upper and lower bounds can actually be quite complicated in practice. But they typically tend to ask them in textbooks where the upper and lower bound are on one endpoint. But in principle, they could be in the middle, in which case you would have to concern yourself with that. So left bound on this side of the graph for the side that is the larger side, overestimating the sizes of our rectangles. And then when we get to the minimum, then we flip over, the larger side is on the right side. And so we'll get a consistent overestimate. Again, the idea here is that you estimate using the smallest possible value, you estimate using the largest possible value. And then as n increases, these values get closer together until they converge to a common limit. Now, in principle, that is going to work regardless of whether you take an overestimate or an underestimate consistently. All of these methods, as n increases, will eventually converge to the same value. But in terms of doing the proof, generally they do a squeeze theorem idea where you have something that's definitely lower, it's underestimating, something that's definitely higher, it's overestimating, and then you show that they come together. Whereas the right bound, left bound, and midpoint rule, you don't have that extra, you don't really know whether they're overestimates or underestimates or how they're going to change per se relative to each other. And unless the function is monotonic, in which case it reduces to an upper or lower bound. So this is the idea behind what we're doing. We're basically estimating rectangles, and then we're adding them up in order to estimate the area in particular ways. Now, it's worth keeping track of these different methods because in the textbooks, on exams, you will get asked to apply different methods. And so at least being able to draw them if you need to in order to make sense of what's going on will be important. Now, what I want to do next is I actually want to just do the calculations sort of from a mechanistic standpoint. And in that context, we're going to stick with right-hand rule, left-hand rule, and then I'll talk briefly. I won't actually do necessarily all the calculations all the way, but I'll talk briefly about the setup differences for the left-hand rule, or for the midpoint rule. Now, the right-hand rule and the left-hand rule are basically going to be the same procedurally until you actually choose your combinations of which function points are you selecting. So we'll kind of do those somewhat simultaneously, and then the midpoint rule we'll do the setup for, and then you will finish it the same way as the other methods. All right, so here's our definite integral version of our problem. The area under the curve is given by the definite integral, and then the upper and lower bounds for the integral are provided here. And then we're specifying n equals 8 rectangles. And then the area is given by, this is the height of the function at some point, and we are multiplying then by the base, which is the width of the rectangle, which is delta x. And then we're calculating the rectangle height times width, adding them all up. That gets us our area estimate. So this formula is always going to be the same, basically. The only thing that's really going to change is that in the right-hand rule, we use x sub I. And in the, typically what we call it, in the left-hand rule, you could either renumber them or you would use x sub I minus 1. And then again, in the midpoint rule, it's probably easier to renumber them than to mess around with the formula, but you're evaluating the function at some point after that. And then x sub I is the value that you're choosing to do the estimation at. All right, so we previously calculated delta x to be b minus a over n, which is equal to 2 minus negative 2 over 8, which reduces to 1/2. So that is step 1. I don't know what happened there. So that's step 1. Now, the second thing that we have to do to make this a little easier for us is we have to find our x sub I. Now, the general rule here is that x sub 0 is equal to a, and then x sub n is going to be equal to b. So in our example, x sub 0 is equal to negative 2. And then each point after that is going to then add delta x. So x sub 1 is equal to negative 2 plus delta x, which is going to be negative 2 plus 1/2, which is negative 1.5. And then each point after that, we keep adding 1/2. So then x sub 2 is equal to negative 1, and x sub 3 is equal to negative 1/2 or 0.5 if you prefer. X sub 4 is equal to 0. X sub 5 is equal to 0.5, that's 1/2. X sub 6 is equal to 1. X sub 7 is equal to 1.5. And then, of course, we get to x sub 8, which is equal to 2, which is our final value. And so I'm just going to list these in a set in order so that I can refer to them more easily. Negative 0.5, 0, 0.5, 1, 1.5, 2. All right. So those are our values. Now, for the right-hand rule, use the values highlighted. So these are the values that are sort of the bounds of our intervals. We're going to use the right-hand version of these, which is going to skip the first value, because that's the left side of the first rectangle. And then we're going to start with the right side of the first rectangle, which is bounded by these two values. And we're going to choose the rightmost one. And then the next rectangle is bounded by these two values on our graph. And we're going to choose the rightmost one, and so on and so forth. So we're going to use all of these values except the first one when we evaluate our function. And then the left-hand rule we're going to use the values highlighted in this next. So the first rectangle is bounded by these two. We're going to use the left one. And then the next rectangle is bounded by these two, and we're going to use the left one. So the left-hand rule uses all of these values except the final value. So these are all the places where we're going to evaluate our function to find the height of our rectangle. That's really the only difference between the right-hand rule and the left-hand rule, is just that in the right-hand rule, you skip the first value, you use all the others. In the left-hand rule, you use all of them except the last one. And then step 3 is we're going to evaluate the function at the given points, the x sub I that we've chosen. So for the right-hand rule, we're going to evaluate f of x sub I, the ones that we need for our problem. And we can, you can use your calculator for this rather than do all the math by hand. I have plugged everything into my calculator, and I'm just going to output the values that come out of a function for the corresponding point. So when I plug in negative 1.5, I get 6.25. When I plug in negative 1, I get 4. When I plug in 2.25, when I plug in negative 0.5, I get 2.25. When I plug in 0, I get 1. That's clear. When I plug in 0.5, I get 0.25. When I plug in 1, I get 0. When I plug in 1.5, then I get symmetry, 0.25. And when I plug in 2, I get 1. Now, the left-hand rule is going to plug in again, most of these points will be the same, but it's going to start with -2 instead of -1.5. And so the first value is actually 9. And then the rest of the values are the same, except you don't use the last value because that was the right end So what you should have when you check these, if you count them, is you should have 8 values in each of these lists. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 in each of these. So that's the heights of 8 rectangles. So find the area of each rectangle. Now there's an add. Now you can actually do these in two different orders. So you can take your delta x, which is the width of your rectangle, multiply it by each one of these values in your list, and then add them up. Or because the rectangles are all the same width, you can add up the heights and then multiply by the width one time. They give you the same answer. So I'm just going to, for the right-hand rule, I'm going to add up my 6.25 and my 4, and I'm going to multiply by a half at the end. So 1/2 times 6.25 plus 4 plus 2.25 plus 1 plus 0.25 plus 0 plus 0.25 plus 1.25 plus 2.25 plus 1 plus 0.25 plus 0.25, because we can skip the 0. And so I get 1/2 times 15, which is equal to 7.5. And then again, the left-hand rule, same idea, except that now we're adding up 9 plus 6.25 plus 4 plus 2.25 plus 1 plus 0.25 plus 0 plus 0.25 is equal to 1/2 times it's going to give me 23, which is going to be 11.5. Now, again, kind of keep in mind what our graphs look like. We were in the left-hand rule, we were overestimating on the longer side from the minimum. And so this is this is not the largest possible estimate for the area with 8 rectangles, but it is larger than probably what it should be. And then 7.5 is a lower bound because we were underestimating on the side that had more rectangles, and underestimating only on the last 2. And so the true area is going to be bounded somewhere between these 2 values. Now, to talk about the midpoint rule very briefly, what happens when we find our list of values, x of I, for the right or the left-hand rule, those are bounding the interval on either side. And we need to find the midpoint of those values. So for the midpoint rule, start with the same endpoints of each of the subintervals, each of the regions. But then you have to find the midpoint of each interval, each subinterval. So subinterval number 1 is -2 to -1.5. Well, the midpoint of that is halfway between so you can find the average. So one way of doing this is -2 plus -1.5 divided by 2, which is going to get you -1.75. And repeat for all the subintervals. So you can do this forever. Or the second way to find this is after you find the first one, then simply, because they're all equally spaced, simply add delta x to the starting value. Until you get to 8 values. Well, in this case, it's 8 values, so you get to n values. So our values, regardless of which way you find them, are going to end up being, the first one is -1.75, and then if you add a half to that, you get -1.25, which is halfway between -1.5 and -1. And then you add another half to that, and then you're going to get -0.75, which is in between -1 and -0.5, and then -0.25, which is halfway between -0.5 and 0, and so forth. 0.25, 0.75, 1.25, and 1.75. And then again, you double check, you make sure there's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Yes, there's 8 of them. And then evaluate the function at each point in the list. There's only 8 of them, so there's not 9 of them like we had before. So you don't have to leave one out. You evaluate at all of these midpoints and then add up. And what you should get is a value that is halfway in between the 2 previous values we found. This will be a more accurate estimate because we're using the midpoint. It's an overestimate, underestimate in each rectangle combination. And so you will get a little bit closer to the true value. But the value you get should be in between 7.5 and 11.5.